This conference will now be recorded.
So hello everyone. Now we'll begin the third section of today, the fifth of this FDP. So the topic of this lecture is the artificial lifting of oil, represented by myself. So artificial lifting of oil is a very important part of the upstream petroleum technology. So as you know, the crude oil is found in the subsurface, and we have to bring out the crude oil to the surface. So bringing out the crude oil to the surface is known as the production of crude oil. So it is also known as the recovery. Recovery means bringing the crude oil from the subsurface or the petroleum from the subsurface to the surface. So the recovery of petroleum is classified into three categories, three phases: the primary recovery, secondary, and the tertiary. So the primary recovery, the production of petroleum, the oil comes out to the surface by its own, with the help of its own natural energy. So in this way, we can produce about 5 to 10% of whatever oil we have at the subsurface. So this is primary recovery, which takes place by its own with the help of the natural energy of the reservoir. So after the primary energy of the reservoir depletes, then the secondary recovery processes are implemented. The secondary recovery processes includes the injection of water and gas. So in secondary recovery, we are injecting water and natural gas to the subsurface so that it assists the crude oil in coming out to the surface. So after primary and secondary comes the tertiary method, also known as the enhanced oil recovery method. This enhanced oil recovery method is more expensive. You see, it is more expensive because it incorporates the use of different kinds of materials. By materials, I mean it can be energy in the form of heat, different types of chemicals, and also microbes and other things. So compared to the three processes, the tertiary recovery is more expensive because it uses different kinds of exotic fluids compared to the secondary and the primary. So as I told you, the primary recovery uses the natural energy of the reservoir. So natural energy, it can be in the form of the dissolved gas, or you can say it is the different driving mechanisms are there. So these driving mechanisms, they are instrumental in recovering the petroleum. So driving mechanisms include the dissolved gas drive. So as the fluid is produced, the dissolved gas comes out. This dissolved gas, it expands and pushes the oil to the surface. In case of gas cap drive reservoirs, we have a gas here. This is the oil in the subsurface. This is the oil. It is overlain by a gas cap. So as the gas cap expands, it pushes the oil to the surface. Then we have the third type, that is the water drive. In case of water drive, this water, it pushes the oil to the surface. So if we compare the recovery efficiency, the amount of fluid that is produced by this type of driving mechanisms, this water drive is the most efficient one because it the water is pushing the oil, there is displacement, physical displacement of the oil to the surface. So in general, we may have a combination of these drives, like water drive with dissolved or water drive with gas cap. So combination drive, which is a combination of all the three mechanisms, is the most commonly encountered mechanism that we find in the petroleum reservoirs. So secondary recovery, as I told you, it involves the injection of classical fluids. By classical fluids, we mean the water and the natural gas. So it can be classified as the crustal gas injection, the peripheral water injection, and the water flooding. In crustal gas injection, we are injecting the gas from the surface into the crest of the reservoir. So this gas, as it is injected to the surface, it pushes the oil to the surface. In peripheral water injection, we inject the water along wells which are in the peripheral region of the oil reservoir. So it's called the peripheral water injection. Sorry. In case of water flooding, what we do, we inject the water into the oil zone. From the surface, these are called the injection wells. We inject the water, and this water, it pushes the oil to the surface like a piston pushing the, it's like a piston pushing the oil. So water flooding is a widely used method, and it involves the injection of treated water. The water is treated, the water that is produced from the formation is treated, and then it is injected back into the oil bearing zone so that the fluid can be displaced. So this injection of water is done with the help of injectors, also called the injection wells. These injection wells and the producing wells, they are arranged in a particular pattern. So water flooding is also known as the pattern water flooding. So this is a schematic of the water flooding process. The treated water is injected. It sweeps the oil, it mobilizes the oil, and then it is produced at the surface. Produced means the fluid is taken to the surface. And this is the artificial lift method. We'll discuss in the slides. In the next slides, we will see what artificial lift is. So these are the injectors. As I told you, the water is injected and it is produced through these are the injectors, and it is produced through the producing wells. So they are arranged in a particular pattern. So it is also called the pattern water flooding. So there are different types of patterns, geometrical patterns, in which the injector and the producer, they are arranged. So it may be a normal 5-spot pattern, 4-spot pattern, regular, or screwed. So the third type of recovery or producing the crude oil, how we produce is using the different kinds of fluids. Like as I told you, thermal, the heat can be injected into the reservoir. We can inject gas, chemicals, and others. So this is the thermal method. It is more expensive than the other, also more complicated for implementation than the primary and the secondary recovery methods. So the primary and the secondary, by primary and secondary, by the reservoir own natural energy, and also by the use of gas and water, we can produce about 34% of the oil in place. That means whatever was there in the reservoir, about 34% of it can be recovered with the help of the primary and the secondary recovery. Now, how do we produce the well? As I told you, it can be the fluids can come up to the surface by its own, or we can use the we can help the reservoir energy. So those methods that use or assist the natural energy of the reservoir in producing the fluid is known as the artificial lift methods. So the artificial lift methods, they involves injecting energy to the bottom of the well. To the bottom of the well, some kind of energy is injected, but we are never injecting the energy into the well. We are injecting into the reservoir, but we are injecting into the bottom of the well. And this is done in order to supplement the natural energy. We are supplementing, we are helping the natural energy to produce the fluid. Now, artificial lift is employed for mainly three reasons. One is when there is the reservoir energy is low. When the reservoir energy is low, the fluids will not come to the surface by its own. In those cases, the artificial lift methods, they are implemented so that the fluids can be produced to the surface. And it is also used, the artificial lift methods, when we want to increase the rate of production, when we want to increase the amount of fluid that is coming out to the surface. To increase the production from the well, the artificial lift methods, they are also used. In other cases, in case of gas wells, in gas reservoirs, in those cases, the artificial lift is used in order to remove the water from the gas wells. Sometimes what happens, the water enters into the well bore and it hinders the production of the gas. In those cases, the water is removed from the well in order for the gas to flow its own. So it is called dewatering of gas wells. So artificial lift method, it is used for three reasons. One, to assist the reservoir pressure in taking the fluid out of the well from the reservoir, to increase the production, and also to dewater the gas wells. So there are several types of artificial lift methods that are used in the petroleum industry. So to mention a few, it is gas lift, where we are injecting gas. Then hydraulic pumping or jet pumping, we use the hydraulic energy in order to bring the fluid from the bottom of the well to the surface. Then plunger lift and the chamber lift methods are also used, but these are just modification of the gas lift. There is another other kind of artificial lift method, that is the sucker rod pumping. The sucker rod pumping is a widely used method. The electrical submersible pumping is also used, the progressive cavity pumping. So in this presentation, we'll shall be concentrating on gas lift, the sucker rod pumping, and the electrical submersible pumping. So if we see the data, the global artificial lift, the implementation, we see that this rod lift means the SRP. SRP is widely used, the ESP, that is the electrical submersible pumping, they're widely used, and also the gas lift. And the major players are the Schlumberger, the GE, the Weatherford, Baker Hughes. They are the companies that are implementing this artificial lift techniques. They are servicing and also implementing. And by region-wise, it is North America that is implementing most of the artificial lift techniques, followed by Asia Pacific, Eurasia, etc. So now we will see what gas lift is. So as the name implies, the gas lift, we are using gas. By gas, I mean the natural energy, I mean the natural gas. Natural gas is used in order to lift the oil. So energy in the form of compressed natural gas, it is injected to the bottom of the well. So this is a well, schematic of the well. So in case of gas lift, we are injecting gas from the surface so that it assists the natural energy of the reservoir in producing the fluid. So this is a network of the gas lift system. You see, these are the different wells. These are the different wells. The fluid that is produced from the different wells, they are collected in the gathering station. The oil is separated from the gas here. Oil goes to the storage tank. The gas, it goes into the compressor station, from where it goes into marketing, and also some part of the gas is injected back. This is the injection gas. It comes into the injection gas manifold. From here, it is transmitted to the different wells. There is a metering and control here. The right amount of gas at the right moment, it is injected or it is transported into the different wells. So this gas that is transported from this manifold, it goes here to the surface. It is connected through the lines. It is injected into the well. It is injected into the annulus. We'll see what annulus is. This is the well. We have the casing here. We have the tubing here. In between, there is a gap. So this gap we call the annulus. So the gas that we are injecting, the natural gas, it is injected into the annulus. It is injected into the annulus. And with the help of different valves, there I'll see in the next slides that there are gas lift valves. With the help of the gas lift valves, this gas is injected into the tubing. We'll see now. So what is the physics here? What is the mechanism of gas lifting? So the gas, the compressed gas, as it is injected, it expands. When it expands, it pushes the oil to the surface. There is also another kind of mechanism, which is the lightening of the fluid column. When the gas is injected, this gas, it mixes up with the crude oil in the tubing. It becomes lighter, and so the bottom hole pressure of the reservoir, can push it up into the surface. So gas lift system, they are classified into mainly into two types: continuous gas lift and the intermittent gas lift. In case of continuous gas lift, this is the continuous gas lift. We inject the gas continuously. The gas from the surface, it is injected into the annulus, into the tubing continuously. There is no break. So this method is called the continuous gas lift. It is used in wells with a high productivity, whose productivity is high, and also whose bottom hole pressure at the bottom of the well, we call it the bottom hole pressure. So high bottom hole pressure, when the productivity of the well is also high, the continuous gas lift is used, where we are injecting the gas continuously into the well. The fluid production in this type of continuous gas lift, it ranges from 200 to 20,000 barrels per day. And if we are using, if there is no tubing, we are using a casing flow, then the flow rate can exceed up to 80,000 barrels per day. So the intermittent lift, this is unlike the continuous gas lift. As the name implies, in intermittent lift, we are injecting the water, we are injecting the gas intermittently. At regular intervals that is determined, we are injecting the gas. So the production from the well is also intermittent. It produces for some time, then stops. It produces. The production as well as the injection of gas into the well is intermittent. So this type of mechanism, or this type of system where we inject the natural gas intermittently, is called the intermittent gas lift system. So this type of the intermittent type of system is used in wells which have a high or low. The PI can be, the productivity of the well can be high or low, and when the bottom hole pressure is low, then we have to use the intermittent gas lift. So this is the intermittent gas lift system. In the intermittent gas lift system, we are injecting the gas intermittently. How this is done? This is done with the help of a system called the TCC. At the surface, we have the time cycle controller. This is called the TCC. With the help of the TCC, or it can be done manually also, the gas is injected into the well at regular intervals through the gas leak valves. These are valves that are attached to the tubing. They are called the gas leak valves. So the gas is injected into the annulus intermittently, and this gas, it enters the tubing through the lowest valve, or whichever valve is used for injection. We call it the operating gas leak valve. So it is injected into the operating valve, it enters the tubing, and it pushes this slug of liquid. Slug means the certain column of the well fluid. It's injected below. This gas, it is injected at a high pressure, high volume. So it physically pushes the slug of the crude oil to the surface. So this is a intermittent gas lift cycle where here we have different components: the operating gas lift valve, the standing valve. So in this period, the fluid is allowed to accumulate here in the tubing. Then the gas is injected below this slug of the oil, and it is displaced to the surface. So there is physical displacement of the crude oil to the surface. So this cycle, it can be classified into three periods, three phases. One is the liquid accumulation period. Here the liquid is accumulating in the tubing. The liquid is allowed to collect in the tubing. Then the slug lifting period, where we are injecting the gas through this valve, the operating gas lift valve. It pushes the slug of the liquid to the surface. So this is slug lifting. And afterflow, that means when the slug, it reaches the flow line, this period is called the afterflow period. So an important component of the gas lift system is the gas lift valve. As I showed you in the previous slide, these are the gas lift valves. These are the gas lift valves. So it's called the heart of the installation. The heart of the installation is the gas lift valve. That means if the gas lift valve fails, then the whole system will fail. So the gas lift valve is called the heart of the gas lift system, because it provides the necessary control for producing the fluid. And most of these valves, they are pressure operated. Pressure is required to operate these valves. Now, the purpose of these valves is depending upon the operation, the gas lift valves are classified. So they are mainly used for, some valves are used for unloading. So I will come to it later. So those are called the unloading valves. It is also used for gas lifting the fluid to the surface. So those are called the operating gas lift valves, and also it helps in the injection of the fluids at the deeper depth. So as I told you, based on the operation, the gas lift valves, they are either pressure operated or mechanically operated. But most of the valves, they are pressure operated. They are opened or closed with the help of pressure. By pressure, I mean the injection pressure or the pressure of the reservoir in the form of the production pressure. So according to the application, the gas lift valves, they can be classified as unloading valves and operating valves. Unloading valves, these upper valves, they are called unloading valves. They are used for a specific purpose. We'll see in the later slides. These are used for a specific application. These are not used during normal operation. During normal operation, this operating valve is used. The lowermost valve is used during normal gas lift operation. It's called operating valve. These unloading valves, they are used for unloading the annulus. So there are two types of valves: the unloading valves and the operating valves. So now we'll see the components of the gas lift valves. There are different components of these gas lift valves. At the top, we have the dome. At the dome, this dome is pressure charged. It is charged with nitrogen gas. It is charged with nitrogen gas, and below the dome, we have the bellows. This bellows, they provide an area of influence for the casing pressure. And below the bellows, we have the stem and the tip. Stem, this is the stem, this is the port, this is the main opening of the gas leak valve. So in some cases, there may be a spring. The spring is attached here, the bellows along with the spring, or sometimes the spring is not there. So this is the stem, and this is the port, means the opening of the gas leak valve. The stem, it sits on the port. So there is a check valve also installed here, so that there is no reverse flow. If there is reverse flow, then the unloading process will fail. So in order to prevent the backflow of the fluid, the check valve is also installed here. So I told you there are the uppermost valves, they are called the unloading valves. The uppermost valves, they are called the unloading valves. Why they are called unloading valves? Because they help in unloading the well fluid. So this picture shows the well that is shut in, or after completion process. So in this case, you see the annulus. Annulus is the gap between the casing and the tubing. The gap between the casing and the tubing. Now the annulus is filled with the fluid. It's called a kill fluid, completion fluid, or well fluid. So in order to implement the gas lift operation, in order to proceed with the gas lift operation, we have to remove the fluid from the annulus. We have to remove the fluid from the annulus. So removing the fluid from the annulus is called the unloading process. In unloading process, we are removing the fluid from the annulus so that normal gas lift operation can proceed. So these uppermost valves, they are used for unloading the well. So this is a unloading process. In case for unloading the well fluid, what we do, the gas is injected into the annulus from the surface. It pushes the well fluid. It pushes the fluid here, the annular fluid. This fluid, it U-tubes into the tubing. These gas lift valves are open. Because of the hydrostatic pressure of the fluid, these gas lift valves are open. So as the gas is injected, it pressurizes the annular fluid. So this fluid, it U-tubes into the tubing through the open gas lift valves. So as the gas injection continues, the first gas lift valves, it is uncovered. It is uncovered and the gas injection continues. Pressure is applied on the annular fluid. Then slowly the annular level decreases, it lowers, and then the second valve is open. So this is a critical situation in unloading process where the gas lift number unloading valve number 1 and the unloading valve number 2 is they are open. So the gas lift valves, they are designed in such a way that when this gas lift valve number 2 opens, this gas lift valve number 1 closes. So now the fluid that is injected, it enters, or gas enters through the second gas lift valve. So the process is continued, the injection of gas continues, it pushes the annular fluid and until the operating gas lift valve is uncovered. So in this way, you see that the fluid from the annulus, it is removed. So this process is called the unloading process of gas lift, where we are removing the well fluid from the annulus, the kill fluid, the completion fluid from the annulus, so that normal gas lift operation can proceed. So only after the unloading process is done, only after the annular fluid is removed, the normal gas lift operation can proceed. So the chamber lift installation, this is a modification of the gas lift system. It's a modification of the gas lift system. So it is a gas lift system, only that the system is somewhat modified. So it is recommended in gas lift wells with very low formation pressure. When the formation pressure is very low, then when the BHP, that is the bottom hole pressure, is very low, this type of gas lift system is used, chamber lift. Now there are two types of chamber lift installation. One is the two-packer and the insert chamber. This is the two-packer. We have two packers here. So the packer is a component of a gas lift system. It is used to seal the annulus. This is the packer. It is located in between, in the annular space between the tubing and the casing. So this is called the two-packer assembly, where we have two packers here, the upper packer and the bottom packer. So in this way, when it is designed in such a way, then the initial fluid volume, it increases. So there is a bleed valve here. So the fluid is accumulated in the tubing as well as the annulus. In case of the insert chamber, this is used in open hole installations. The bottom of the tubing, it takes the shape of a chamber. It takes the shape of a chamber. So for the same bottom hole pressure, the amount of fluid that is accumulated is high compared to the normal intermittent installation because of the design we have made. Because of the design we have made, the bottom hole assembly, it is modified. Here it is in the form of a chamber and two-packer. The amount of fluid that is accumulating during the accumulation period, it increases. So the production from the well increases. So there is another type of gas lift installation which is called the plunger lift. It's called the plunger lift. So it is also a modification of the gas lift system. It's a modification of the gas lift system. If there is a problem with the intermittent gas lift installation is injection gas breakthrough and liquid fallback. So during the intermittent gas lift installation, as the gas, it pushes the liquid to the surface, the injection gas, because of its higher buoyancy, it enters the bottom of the liquid. So there is some fluid is not produced during the cycle. So this fluid that is not produced, it is called the liquid fallback. It falls and accumulates inside the tubing above the standing valve. So when there is liquid fallback, injection gas breakthrough and liquid fallback, the amount of fluid that is collected, that we recover, is less than the amount of fluid that collected at the bottom of the well. So the production or the amount of fluid that is produced from the well decreases. So in order to remove this injection gas breakthrough and minimize the liquid fallback, a plunger is injected, or a plunger is located, or plunger is installed between the, this is the gas, this is the liquid. So a plunger is installed in between the gas, injected gas, and the fluid. So the cycle of operation is same like the intermittent lift, only that there is a plunger in between the gas that you are injecting and the fluid. So this plunger, the gas is injected. The plunger is it has a free piston type. It has a bypass valve inside. So when it lands on there's a bumper spring at the bottom of the well. So when it hits the bottom during its fall at the bottom of the well, the bypass valve, it closes. So when the gas is injected, the gas, it pushes the plunger, and this plunger in turn pushes the liquid to the surface. So in this way, the injection gas breakthrough and the liquid fallback is minimized. Again, when this plunger, it goes to the surface, the it hits the lubricator. There is a lubricator system here. It hits the lubricator. There is a catcher mechanism here. When it hits the lubricator here, the bypass valve, it opens. When it opens the plunger, it falls down. It falls down. So this plunger is free to move up and down. So there is a lubricator here. This lubricator is used for catching the plunger. Sometimes the plunger is to be catched, and also that it can be repaired. So this lubricator is used for removing the plunger and repairing it. There are also the bumper springs. These springs are instrumental in absorbing the kinetic energy and also in closing the valve. There is also another spring here in the catcher mechanism, which it for the fluid, the plunger, it moves at very high speed. It catches here, it gets here, and it hits the catcher mechanism, falls down, and the system and the process continues. So one advantage of this plunger lift is that, another advantage, that if there is any deposition of fluid in the tubing, by its movement up and down, it is removed. Any deposition in the well tubing, it is cleaned. So next we come to the other type of the artificial lift method, the sucker rod pumping. Most of you have seen this type of instrument in the oil fields. It moves up and down. So this is called the sucker rod pumping. This is another type of gas lift system. I mean another type of artificial lift system, the sucker rod pumping. So it is the oldest and the widely used artificial lift method. It is the oldest. Now in US, the 85% of all the artificial lift wells, they are produced by the sucker rod pumping. In short, we call it as SRP. Now we'll see there are different components above the surface and also below the surface. So the main components of this sucker rod system, it works on the principle of a hand pump. We use the hand pump to pump water. The principle is same. The same principle is used in case of sucker rod pumping, the principle of a hand pump. So the main parts of the sucker rod pumping system are the surface unit, the sucker rod string, and the subsurface equipments. So you see there are different types of the surface pumping unit, has different components. So this is the prime mover. It gives the power to the system, driving power to the system. So it is an electrical motor or an IC engine. It can be a electrical motor or an IC engine. But most of the sucker rod pumping units, they run on the electrical motors. The electrical motor's advantage is that its cost is low, and also the maintenance cost. The control is, the ease of control is there, and it is more compact. So electrical motors that are used are squirrel case induction motors with low speeds around 720 RPMs. So alongside the prime mover, we have the gear reducer. There is a gearbox here. There is a gearbox here. The function of this gearbox or the gear reducer is to reduce the high rotational speed of the prime mover. High rotational speed of the prime mover, it is lowered, it is reduced in the gear reducer or the gearbox. This prime mover, the speed is around 500 to 1500 RPM, whereas the sucker rod string, it moves, its speed is around 10 to 20 strokes per minute. So the high speed of the prime mover is reduced to the low speed of this sucker rod string with the help of the gear reducer. So inside the gear reducer, we have the power is transmitted with the help of V valves, there are sieves. So the speed reduction, it takes place because of the sieve and also because of the ratio between the gear reducer sieve and the motor sieve. So there is also inside a double reduction gearbox where the speed is reduced to about 1:30. So this high speed of the prime mover, about 500 to 1500 RPM, is reduced to low speed, that is about 10 to 20 strokes per minute, with the help of this gearbox. So the function of the gearbox is to reduce the speed of the prime mover to the pumping speed. So we have the crank arm here. This is called the crank arm. This is called the crank arm. This is called the crank arm. This portion is called the crank arm. So this is called the crank arm, and we have this what is called the walking beam, and this post is called the Simpson post, and there's a bearing here. So this is called a saddle bearing. So this crank arm is rotating. It's rotating. So the rotary motion of the crank arm is converted into linear motion of the sucker rod pump with the help of this mechanism, consisting of the beam, the walking beam, the Simpson post, saddle bearing, and the pitman arm. So the crank arm is connected to this walking beam with the help of the pitman connection. There is a pitman connection here. So on this side we have this is like a horse head. So this part is also called the horse head. This horse head, it is connected to here we have the cable, sucker rod cable, sucker rod string we called it. So the sucker rod string is attached here to the horse's head. So this is a polish rod. There's a stuffing box for lubrication it is used. So this polish rod, it takes the whole load of the sucker rod string. It takes the whole load of the sucker rod string. So this is about the surface pumping or surface units of the sucker rod pumping unit. Now we'll see the subsurface units or the sucker rod string. So from the energy from the surface is there we have a sucker rod pump. There is a positive displacement pump, PD pump here, which is used for pumping the fluid. So the energy from the surface to the pump is transmitted to the sucker rod string. To the sucker rod string it's assembly of sucker rods. So sucker rod string is an assembly of the sucker rods. Different sucker rods, they are connected. These are individual sucker rods. They are connected together with the help of the coupling. They are with the help of coupling. There are bearings here. I mean, there are threads here. The couplings are connected here. So the sucker rod strings, they are available in different sizes, different diameters, 5x8, 3x4, 7x8. They are all common. So the lengths can also vary, about 25 feet, 30 feet, 35 feet, but the 30 feet is common. There are also smaller sucker rods are also there. I mean, the length of the sucker rod is about 2 feet. So those sucker rods, they are called the pony rods, pony sucker rods. So the sucker rods, they are connected together. They form a string. They form a connection from the surface to the subsurface. So they are connected together with the help of the couplings. We have couplings here. They are used for connecting the different, I mean, the sucker rod strings, the individual sucker rod strings, I mean sucker rods. Then we come to the subsurface components. We saw what the surface components are. We'll see what the subsurface components of the SRP unit. The subsurface, the components that are down the surface. So the subsurface equipments include the tubing string. This is the tubing string. So I want to tell you that this is a tubular that is used for producing the fluid. So it is called the tubing string. The tubular that is used for producing the fluid, that is taking out the fluid from the subsurface to the surface, is called the tubing. That is the production tubing. So production tubing, this is the casing. Casing is used. So the tubing and the casing, they are the downhole components of the sucker rod system. Then we have the sucker rod string, which is the assembly of the sucker rods. Then we have the pump, the subsurface pump. It's a PD pump, positive displacement pump. So there are four essential components of the pump. They are the working barrel. I'll see in the next slide probably. Yes, there are four components in fact. One is the working barrel, and inside the working barrel we have a plunger. Then we have a standing valve. Standing valve is fixed, it doesn't move. There's a traveling valve which travels along with the plunger. Then there are tubing anchors. These are called the tubing anchors. These tubing anchors, they are used for anchoring the tubing with the casing. Because the fluid is taken to the surface, the production tubing, it takes the load of the fluid. Thousands of feet of the fluid, the weight will be very high. So the tubing, it can stretch. In fact, the load is transmitted from the tubing to the string. So when the load is taken by the tubing, it stretches, and when the load is transferred to the sucker rod string, it contracts. So this potential movement is prevented with the help of the tubing anchors. These are the tubing anchors. These tubing anchors, they allow the fluid to flow through the annulus, but they are preventing the motion of the movement of the tubing. So this is a very important part of the downhole component. Now sitting nipples, these are just the reduced diameter sections of the tubing, I mean the tubing and the casing. So another important part is the separators, the gas and the mud anchors, and the bottom hole separators. The gas and the mud anchor and the bottom hole separators, they are used in order to separate the gas from the liquid. If there is gas coming along with the crude oil, then the efficiency of the pump decreases. The efficiency of pump, the ability of the pump to pump the required amount of fluid from the subsurface to the surface, it reduces if the fluid is laden with gas. So in order to remove the gas from the liquid, the bottom hole separators and the mud anchors are used. So the bottom hole separators, they are just tubings where the fluid is allowed to flow through the zigzag path. When the fluid flows through the zigzag path, because of the changes in direction, the gas, the free gas, it gets out of the fluid. So this free gas, it moves outward, and only the gas-free liquid, it enters the sucker rod pump. So mud anchors, they also function the same, is also used for the same purpose, for removing the gas that is entering the pump. So for removing the gas that is coming along with the free gas that is coming along with the liquid, they are separated from the liquid, so that the pump is only pumping gas-free liquid. If the gas enters here, the efficiency of the pump decreases. So this is a pumping cycle. As I told you, there are different components. The working barrel is there. This working barrel is fixed to the tubing here. Inside the working barrel, we have the sucker rod string. The plunger is here. The traveling valve moves along with the plunger. There's a standing valve here. So this point, it shows that the sucker rod string is moving down, the traveling valve is open, and fluid is collecting inside the tubing. Now in the upstroke, this is called a downstroke, this is upstroke. In the upstroke, the traveling valve is closed. It is closed here. The fluid is removed from this, or it is pumped to the surface. So now the load of the fluid is taken by the sucker rod string. So as it moves up, it delivers the fluid to the surface. It pushes the liquid to the surface. This is the upstroke. During the downstroke, this standing valve, the traveling valve opens. This plunger, it goes down, and this standing valve is now closed. So this is a cycle of the SRP operation in the downhole section. So the selection of this SRP system, they are used when the operating depth is around 100 to 11,000 the total vertical depth. The volume of lift is around 5 to 1500 barrels per day. The operating temperature is typically in the range of 100 to 350 Fahrenheit. So for gas handling, it is fair to good. The solid handling also, it's fair to good. The API gravity should be greater than, it should be light. I mean, it should not be heavy crude. And for servicing, we are to use a workover rig. So the efficiency of the system is around 45 to 60%. Next comes this is the electrical submersible pumping. The electrical submersible pumping is a widely used method of artificial lift. So this method of lift, we are using a submersible pump. So it is said to be the most versatile artificial lift methods for higher production rate. When higher production rate is required, this method is widely used. So it can be used for fluids which are of low viscosity like the water. It can also be used for fluids with high viscosity also. This is unlike the SRP. And in some cases, when the wells are very deep, more than 15,000 feet, this method can also deliver the purpose. So the production rates of this ESP ranges from 100 to 90,000 barrels per day. So now we'll see the different components of this ESP, that is the electrical submersible pumping. So again, the components, they are classified as surface and subsurface components. So in the surface, we have the power source. Power should be provided. There is a transformer here for stepping out the voltage. So most of the submersible pumps, they use high voltage. So in order to step up the voltage, the transformer is used. So when the voltage is stepped up, you know, the lower currents can be used. When lower current is used, the size of the conductors, that is the cable, lower size can be used, smaller size can be used. Then we have the switchboards. Switchboard, they provide the switches and the controls. And the controls here in the switchboards to control the operation. Then we have the junction box. This is called the vent box or the junction box. This junction box is located in between the wellhead. This is the wellhead. In between the wellhead and this is the switchboard, the vent box or the junction box is installed. So the purpose of this vent box is to prevent a fire hazard. Sometimes what happens, the gas, it may come along with the cable. There is a cable here for transmitting the electrical energy from the surface to the motor. So the gas can come along with the cable. If there is no vent box, it can go into the switchboard. If there is so there may be a fire hazard. So in order to prevent the flow of the gas into the switchboard, there is a vent box here. This vent box, it vents out the gas. It eliminates the gas travel is eliminated. So it is installed about 3 to 4 feet above the ground. Then we have the surface cable. The cable is there. Surface cable. This cable is used for transmitting the electrical energy from the surface down to the motor. The motor needs to be run, and we should provide the electrical energy. So this electrical energy is conducted from the surface down below through this cable. So the cables, it can be round cables or flat cables. In portions where the annulus is of the size is small, the gap between the tubing and the casing is small. In those sections, the flat cable is used. In other sections, you can use a round cable. So these are the surface component of the electrical submersible pumping. Now we'll come to the subsurface component. The subsurface component includes the pump, the cable, motor, hydroprotector, and the intake section. So we now see the motor. So there is a motor here, there is a submersible motor here. The electrical energy runs the motor. So this is a submersible motor. It's a two-pole, three-phase squirrel cage induction motor. It runs about at a nominal speed of around 3,500 RPM, and it is filled with some kind of oil to provide the lubrication and the thermal conductivity. Now the heat that is generated, now when the motor runs, the heat is generated. And this heat is transferred to the well fluid. The well fluid, it is coming to this portion. So the heat that is generated in the motor due to its running is transferred into the well fluid through the oil. There is oil inside the motor. Through the oil, via the oil, the heat is dissipated into the well fluid. So this motor, it should be installed above the perforations. Perforations means, as in the morning, Mr. Deka told you that there are perforations. We use some explosive in order to provide holes in the tubing. So those are called the perforations. These perforations, the motor, it should be installed above the perforation. So when the fluid comes here, it can provide the cooling action. So the heat that is generated inside the motor, it can be dissipated into the liquid. So these motors, they are manufactured in different sizes. It can be about 3.75 inch to 7.38 inches. So the motor selection is depending upon the size of the tubing that you are using. So depending upon the tubing size, the maximum OD of the motor can be selected. So above the motor, we have the seal section, protector or the seal section. This above the motor, we have the seal section. This seal section, it connects the motor to the pump. The thrust bearing, there are thrust bearing here, high capacity thrust bearing. So it connects the motor to the pump. And also it acts as a reservoir of oil. Now when the motor rotates, the oil can expand because of the heat, temperature heat generated, the oil expands. So this oil, it goes into the seal section. The seal section, as I told you, it acts as a reservoir. And when the motor requires to be cooled, then this seal section provides the extra oil for cooling the motor when it is stopped. So this seal section is a very important part of this subsurface component. Now above the seal section, we have the intake section. Intake section means where the well fluid enters. The well fluid enters here. So in here we have the separators also. It is below the pump. This is the intake section. In this intake section, we have the bottom hole separators. Like the SRP, here also the bottom hole separators are installed. The function of these bottom hole separators, as I told you, is to free the gas. It is remove the gas that is coming along with the fluid, so that only gas-free liquid enters the pump. So the separator and the intake section, they are the same. Inside the intake section, we have the separators to separate the gas from the liquid, so that only gas-free liquid enters the pump. So the pump it's a multi-stage centrifugal pump. Multi-stage centrifugal pump is used. A number of stages can be used depending upon the pressure we require. Depending upon the pressure that is required to push the liquid to the surface, the different stages can be used. So each stage of the centrifugal pump, it consists of an impeller that rotates inside a stationary part that is called the diffuser. So each stage of the centrifugal pump, it adds a little pressure. So there are a number of stages. So by the time it reaches the top, the pressure is increased to a level sufficient enough for the fluid to be lifted to the surface. So there are other components also, like the check valve. This check valve is here. Check valve, you see, this is a check valve. It is located 2 to 3 joints of tubing above the pump. Above the pump, the check valve is used. The check valve is used to prevent the backflow of the fluid. Is used to prevent the backflow of the fluid. So when the pump is not running, the fluid may flow back. So if there is no check valve, or if the check valve fails, then the fluid will backflow and the motor bearings can be, or motor can burn, there can be bearing failure, and also the shaft can be twisted. So the check valve is used to maintain a fluid level in the motor so that there is no backflow of fluid into the pump. So above the check valve, there is a drain valve. You see, there is a drain valve here, check valve. It is this drain valve is used to drain the liquid. Suppose we want to take out the tubing. We want to take out the tubing. So taking out the tubing as well as the fluid inside, it will be very heavy, thousands of feet of fluid. The weight will be very heavy. So the fluid is drained from here. Is drained from here so that we can lift the empty tubing. So the weight that is to be lifted decreases. So there are other components also, like the centralizers. Some centralizers are used so that the pump is centralized into the tubing. In the tubing, inside the tubing, it is centralized. So these are the different components of the ESP. So the advantage of this ESP, as I told you, it's a high volume gas lift system. It can produce over 1,000 barrels per day. The maintenance cost is low. The surface equipments are also not that major. And it can be used in deviated wells. In case of crooked wells, in case of wells which are not vertical, the application, it gives good results. Now, there are some disadvantages of ESP also. In case of multiple compressions, where the fluid is coming from different zones, this system is not very applicable, or it does not give good results. And also electrical power and high voltages are required. And also it is very expensive to change the equipment. The handling tubulars of it is also difficult because the cable is there. And gas, if it comes, then the efficiency of the pump decreases. So we have to take care that gas, if there is gas, then the efficiency of the system decreases. And the cable that is used for transmitting the electrical energy from the surface to the pump, it has to undergo high pressure, so it may deteriorate under the high pressure of the well. So applications, it is used in depths of 1,000 to 10,000 feet. It can be used. It's a high volume mode of artificial lift system. The operating temperature is also high, 100 to 75 Fahrenheit. Corrosion, it's good to handle corrosion. The gas handling is, I told you, gas should not be, if gas comes, then the efficiency of the pump decreases. Then the system efficiency is around 35 to 60%. So that's it. That's all about the artificial lifting of oil. So we saw that the artificial lift methods, they are used in order to pump the liquid or to bring the liquid from the subsurface to the surface. So different types of artificial lift methods are there. Gas lift, we are injecting the gas. The SRP, which operates on the principle of a hand pump. The ESP, we use a multi-stage centrifugal pump. There are also other types of artificial lift methods like the hydraulic lifting, the gas, the jet pumping, the PSP, that is the progressive cavity pumping, is also there. Thank you so much. So if you have any queries, you can please ask, or you can type in the chat box. So if there is none, we said end the session. So this is the third session of today. So we have come to the end of the day 2.
Is it audible?
Yeah.
Hello, sir.
Yeah.
Yes, sir. Sir, I just want to ask you just one question. Like, sir, as you have mentioned that in case of ESP, it is used for deviated wells. So, like, sir, can you just compare with SRP, like, which will be much more convenient? Like, so why ESP will be much convenient to use for highly deviated wells?
Deviated wells for SRP, deviation is a problem because we are in the guard string. So if there is a deviation, the string may detach, the string may be broken down, it can be damaged. But in case of ESP, the pump is pumping the fluid to the surface. So deviation is not a problem in case of the ESP. There is a centrifugal pump. This centrifugal pump down below, it pumps the liquid fluid because there are different types stages of this centrifugal pump. So the pressure is increased to a level so that the fluid can be lifted to the surface. So the deviation does not cause a problem in case of ESP. But unlike this ESP, the SRP is when there is deviation, the SRP will be problematic because we have the string there. The string cannot go inside the crooked holes. So there will be problem. The string can damage, and also the efficiency of the pump will decrease.
Okay, sir. Thank you so much, sir.
Thank you. So that's it for today. So we'll wind up here. So on the behalf of Department of Petroleum Technology, I thank all the participants for joining this day 2 sessions, and sincere thanks to the resource persons also for sharing their knowledge and expertise through their talks. So please join me again tomorrow at 10:30 for the third day. Thank you for joining. Thank you for your patience hearing. Have a nice evening. Thank you.